respect to function and domain topological space, we can define topology on the codomain. So that is the quotient topology. So let us quickly revise the last lecture and then we will go forward. So here A is a given 3-element set, and we consider P function from R to A, and on the domain R we define the standard topology. So using this function P, the way it is defined, and the standard topology on R, we have defined a specific topology on A. So that topology is the quotient topology, and how it is defined? It is defined in this way, that a subset V of codomain A is open. That means it belongs to the topology tau if its inverse image P inverse V is open in the domain. So domain is R with the standard topology. So P inverse V is open in the standard topology. Then we say V is open subset of the codomain. So for this example, since P takes only 3 values, so the codomain A has 3 elements, so all subsets will be 2 power 3, and all the subsets we have actually found its inverse image, and we have checked whether it is open or not. So in this way we have we found all the open subsets of codomain A. So there are only these 5 sets which are open subsets of A. So they are elements of the quotient topology, and this quotient topology depending on what is the definition of function P and what is the domain, and what is the topology on the domain. So every function from a topological space to codomain gives us a topology on codomain which is known as the quotient topology. And with respect to quotient topology, P is always continuous, because the way we are defining this topology, it automatically makes the function P continuous. Then we studied 2 main examples. One is open set and one is closed set. So set is open if image of open set is open. So for the continuous function, we have other conditions, that inverse image of open set is open. But for the function to be open map, we need this condition that image of open set is open. Same way, the function will be closed if image of closed set is closed. And as in the case of continuous function, we can get this result similarly, that if I know the basis of the domain space X of the function f, then f is a open mapping or open map if and only if image of open set is open in the codomain Y. Image of the basis element is open in Y for every basis element B. So we proved more or less, we already know this proof, what we use for the continuous functions. And then we observe that the projection map on the product topology is open map, but it is not closed map. And at the end we define quotient map. So what is the definition of quotient map? A map is called quotient map if first of all it should be onto function f from x to y, and x and y are topological species. So what this says in simple words is that if on the space y, if I have a topology tau y, then V belongs to tau y if and only if f inverse V is open in X So that means basically f inverse v belongs to tau x. So if you recall, so this is meaning of the map is open, right? Sorry, the map is quotient map. So let's start today lecture with this. A function f from x to y is a quotient map if the following holds. So what is the definition of quotient map? Definition of quotient map is that v belongs to tau y if and only if f inverse v belongs to tau x. So let us have a remark. So we know that f is continuous if we have this property, v belongs to tau y implies f inverse v belongs to tau x. So if this property is satisfied, then f is continuous. So what is difference between these two property? Here I have here I have implies and here I have if and only if, right? So basically this is a stronger condition. So what is the remark is that therefore every quotient map is by definition continuous map, because it satisfies a stronger condition. Okay, so let us see some one or two simple examples. So if I consider a subspace topology on the set 0 1 union 2 3, induced as a subset of real line. So here real line means basically we are considering standard topology on R. So this is the domain X, and similarly we can consider the closed interval 0 to 2 with the subspace topology on Y as a subset of R, and on R we have again standard topology. So basically if you recall the subspace topology, then what is the subspace topology? A set which is open if it is a intersection of open interval with Y, right? The same way, a subset of Y is a basic open set if it is a intersection of basic open set of real line with Y. So open sets means union of basic open sets. So what is the function here? So the function which we are defining is a P from 0 1 union 2 3 2 0 2 which we are defining as P of x equal to x for all x in the first interval, and it is x minus 1 for all x in the second interval. So what shall be the graph of this function? Let us first see that. So graph of this function will be, so domain is 0 to 1 and from 2 to 3 close interval. So on 0 1 the function is identity function, so it will go up to 1 point, and then after that it will start from 2, and at value 2 it takes value x minus 1, so that is 1. So it will start again from this point and it will go at 3, it will take value 2, and this is equation of line, so therefore we need to join it as a line segment. So this is graph of the function. So these both points are at the same height, right? So this is graph of P. So from this graph we can easily see that this function is onto. So note that P is onto function. And secondly, what we can see here is P is continuous also. So P is continuous. So what is the definition of continuous function? Can we recall again? If I have two topological spaces, then the given function is continuous if inverse image of open set is open. So so that to check that, what we need to check is you take any open set of the interval 0 to 2. So when you take any open interval, so basically in the subspace topology it will be of this form. So let us say this is interval AB. So when I intersect 0 to 2 intersection AB, so what I will get is, if A is between 1 and 2, then this will be nothing but the interval A to 2, right? And so this if my A is between 1 and 2. So this is a basic open set. Now what is the inverse image of this basic open set? So if you see this function, then the inverse image of this particular interval will land somewhere here, right? So it will be kind of let's say this point is C, then it will be C to 3. In fact, we know that in the interval 2 to 3 the definition of function is x minus 1. So what it will happen is we have to add 1 in A. So am I correct or I'm doing any mistake? Right, so it is fine. So this will be the interval A plus 1 to 3. Right. So this is inverse image of the basic open set, which is we are getting this set, and then we know that this set is open in the domain. In the subspace topology. Why? Because this is nothing but the intersection of A plus 1 to 3 is intersection of 0 1 union 2 3. So this is domain intersection A plus 1 to, let us say, 4. Right. So this set is open. This set is open in the subspace topology. On the domain X. So here we have checked that we are taking a particular basic open set, its inverse image is open. So same way you can check the other possible basic open sets also. So what are the other possible basic open sets? So in case A is here, right? So that is the other case. The same way you can consider the interval close 0 to A, where A is either here or here. So basically there are 4 types of basic open sets, and over the every type of basic open set, if inverse image is open set, then by definition of the continuous function P is continuous. So we can easily check that inverse image of basic open set is open, therefore P is continuous. So this function is onto, it is also continuous function, and we can also see that this map is closed also. It is easy to check that P is closed. So to check P is closed, the same way we can check, we will consider the all basic closed sets in the domain. So what will be the basic closed sets? So on the real line, we know that closed intervals A to B are the basic closed sets on the real line. So here basic closed sets will be the intersection of closed interval AB with the domain. So we have to check that its image is also closed. So the same way which here we have checked the inverse image of open set is open, we can also check that image of closed set is basic closed set is closed, and that will give us the function is closed. However, the function is not open, so that we can note here that note that P is not open. So why it is not open? Because if we take image of closed interval 0 1, then we'll get closed interval 0 1, right? But what will happen is this is open set in domain in the subspace topology. On the other hand, this is closed set, or you can write it is not open in the codomain. So therefore this is not open, because if it is open map, P is open map, then image of every open set should be open set. But the set which is open in the domain, its image is not open in the codomain. So why it is happening? Just let us go back again to the graph. So why 0 1 is open here? Because our domain is closed interval 0 1 and closed interval 2 3. So closed interval 0 1 we can write as closed interval 0 1 intersection, let us say -1 to 1.5 open interval, right? So therefore this is open in the domain, but that is not open in the codomain, because codomain is this whole interval 0 to 2. So 0 to 1 is basically intersection of 0 to 2. I can not write as open AB for any A and B. Why? Because if I will take any AB, then what I will get is basically I will get the interval at most 0 to open B, right? I will not get closed on the right side. So therefore this set is not open in the codomain. So this map is not open, however it is a closed map. Same example we can consider to study the quotient map. So let us just slightly modify the domain. So take A to be the map 0 1 union open close interval 2 3 as a subspace of R with standard topology, and now consider a function p from A to close interval 0 to, again here we will consider subspace topology as a subspace of R, where R with the standard topology. So this function we are defining in the same way. So px equal to x, for x is in the close interval 0 to 1, and x minus 1 for x is in the open close interval 2 to 3. So we can again draw this graph of this function, only change is we have excluded the point 2, but still you can verify that easily that we can verify easily that p is a contour function, and again it is continuous. So now if I want to check that whether uh, P is the quotient map or not, what we need to check? So again let us recall the definition of the quotient map. So by the definition of quotient map P is a quotient map if and only if we satisfy the property that inverse image of open set is so what is the property if V is open in Y if and only if V inverse V is open in X. So here these both topologies are subspace topology as a subset of R, right? So if we can prove that this property holds for every open subset of codomain, then we are done. Otherwise, it may not be true. So since we know that the codomain is the closed interval 0 to 2, so let us consider a particular open set in that. So note that the interval 1 to 2 is open subset of 0 to in the subspace topology. So if its inverse image is not open, then we will directly conclude that this function P is not a quotient map. So let us check what is P inverse of the set 1 to 2. So since we have defined the P as X in the closed interval 0, 1 and X minus 1 in the interval 2 to 3, the inverse image of 1, 2 will be open close interval 2 to 3. And then we can easily see that this set is closed in the domain. So what is the domain here? Domain here is closed interval 0, 1 union 2 to 3. With respect to the subspace topology. So what happened is we have chosen a particular open set. Its inverse image is not open. Right, so actually this function is not continuous, and we have already seen that the function is not continuous implies it is not a quotient map, because every quotient map is by definition continuous. So therefore P is not continuous, and therefore P is not a quotient map. So I think what I have written is wrong here, because what I have written is it is a continuous map somewhere. So this is wrong actually, because we have verified that it is not continuous function. Because if it is continuous, inverse image of every open set should be open. But for this particular example, inverse image of open set is not open. But if you take the previous example, the inverse image of this set is open, because there, if you remember, we are considering closed interval 0 1 union closed interval 2 3. So therefore this set is open there. But for this particular example, since we have changed the domain, this function is not continuous. Okay. So this is just a simple example which I wanted to discuss. Now there are two simple properties we can discuss about closed set and open sets, closed set and open maps. So we have already noted that for every function f from x to y, f from x to y, we know that f of f inverse v is always a subset of v. Okay, so what is v? V is a subset of y. V is any subset of y. So this we have already verified by the definition of the inverse of set. Right? What is inverse of a set? If inverse v is the set x in x such that f of x is in v. So using this definition, we have verified this property for every function. But the converse is true when only when the function is onto. So this I have given as an exercise in the first lecture. So you may have done it. Let us just recall it quickly. So if f is onto function, then we will get v is a subset of f inverse v. So let us prove this simple part. So let us take any element y belongs to v. So since f is onto, there exists x in x such that f of x equal to y. Alright, f of x equal to y. And if f of x equal to y, that means what? That means x is in f inverse v. Right? By the definition of f inverse v, what are the elements in f inverse v? X such that f of x is in v. So here f of x is y, which is in v. So therefore x is in f inverse v. So that is fx is in f of f inverse v. And then what is f of x? F of x is y. So just simply using f of x equal to y, what we proved is every element of v belongs to f of f inverse v. Right? So converse is true when f is onto. So finally what we proved is if f from x to y is surjective, then for every subset v of y, these two sets are same. F of f inverse v is exactly v. So this is true whenever f is onto, and this is not true whenever f is not onto, because we will not get this if function is not onto. So in that case, one of the set will be null set, so that we can verify easily. So this property we will use in one or two simple results which we derive today. The first result is that first result which we derive today is this be a continuous function, let us say. So then if f is surjective and open map, then f is a quotient map. Similarly, if f is surjective closed map, then f is a quotient map. So this proposition gives several examples of a quotient map. So if I know a function which is open or closed, it is surjective, it is continuous, then it is by definition, by this using this proposition, it will automatically be quotient map. So we will prove the first part and second part is similar, so it will be verified easily. So since f is continuous, whenever v belongs to tau y, we get f inverse v is in tau x. So one condition is satisfied, that v belongs to tau y implies f inverse v is in tau x. Now we want to prove the converse. So if f inverse v is in tau x, we need to show v is in tau y. So that way it will satisfy the definition of the quotient map. So now if f inverse v is in tau x, and we also know that wait a minute. So, and what is f? F is onto open map. So since f is onto open map, what we will get is what we just now discussed. We will get v equal to f of f inverse v, because v is onto, because f is onto. And since f is open map, we already know f inverse v is open and f is open. So f maps open set to open set. So since this is open, this is also open. So using that, this belongs to tau x. It is an open set of x. Sorry, it is open set in y because they are applying f function. So codomain is y. So now we have used both the things. F is onto, that will give this thing, and f is open, that means image of this set is open. So what we finally got is, therefore v is open in y. So therefore the function is a quotient map. what we verified is we verified that V is in tau y if and only if F inverse V is in tau x. So that is the definition of quotient map. So second part we can prove similarly. So this is more or less regarding the quotient map which we wanted to discuss. Now still there is 10 minutes, so let us start some basic definitions related to the next topic, which is connected topological space. So a topological space X is called disconnected. So first of all, we'll define what is a disconnected space, and the space which is not disconnected is a connected. If I can write X as a union of two sets, U1 union U2, where these two sets U1 and U2 are, of course, they are non-empty set and they are open sets. Subsets of X. So if I can find for a given topological space X, if I can find two sets U1 and U2 which are open, whose union is X, and in fact these sets are disjoint open sets. Then X is called disconnected, and if X is disconnected, in this case the pair U1 comma U2 is known as separation of X. So basically it is separating X into two parts which are open. So a small remark which says that now what is happening is U1 is open and X is a union of U1 and U2, right? So if U1 is open and X is U1 intersection U2 and U1 U2 are disjoint, then what is U2? U2 is by definition X minus U1, right? So by definition of this separation, U2 is an open set, right? Note that U2 is an open set by the definition, but U2 is also complement of U1 and U1 is open set, right? So if I have an open set in a topological space, its complement is always a closed set. So what is happening here is U2 is open set as well as it is a closed set, right? So U2 is an open set and U2 is also a closed set. So now you will ask that how can it happen, because if a set is a open set, then how can it be closed set? So you are saying that because of you are considering that as a subset of real line, and real line is not a disconnected space, it is a connected space. So this will not happen in the real line. So before taking example, let me just write down the definition of connected space. A topological space X which is not disconnected is called a connected space. So let us take some examples. So first example is X equal to R with the standard topology. So first let us assume that X is not connected. So suppose X is disconnected. So if X is disconnected, therefore I can write X as a union of U1 and U2, where U1, U2 are non-empty, disjoint, open subsets of R with respect to the standard topology. So, so what I will get? I will get from that remark that therefore U1 is open set. One subset of R. And then we know from real analysis that if I have an open subset of R, it can never be a closed subset in the real line, right? So we know from real analysis that U1 cannot be a closed set. So the set which is open cannot be a closed set if it is a non-trivial set. If it is a null set, so for example, I consider U1 to be a null set or U1 to be the whole real line, then its complement is open because the complement of phi is whole R and complement of R is null set. So in that case, we can write X as the union of phi union R, but in that case, phi and R are phi is empty set, so it will not work because the condition is that U1 and U2 both should be non-empty sets and they are disjoint. So such a thing is not happening in the real line. Therefore, R is connected. So so let us stop here today lecture because already we are